Chapter 1. A World in Motion. Before Einstein, the universe was a clockwork machine, precise, predictable, and absolute. Time ticked forward at the same pace for everyone. Space was a passive stage where events unfolded, and the laws of motion seemed carved in stone. But then, cracks began to form in this perfect picture. In the late 19th century, physics was considered nearly complete. Sir Isaac Newton's laws had reigned for over 200 years, explaining everything from the falling of an apple to the motion of planets. His idea was elegant. Space and time were absolute, fixed and unchanging, the solid framework of reality. Objects moved through this static arena according to universal laws, and gravity, that was an invisible force acting at a distance. It worked incredibly well, but something was off, and it would take the sharp mind of a young patent clerk to see just how deep the problem went. Let's rewind for a moment. In Newton's world, if you're sitting in a stationary train and someone walks past you, you measure their speed relative to the train. If the train starts moving, and they walk in the same direction, their speed relative to you changes. That's simple. Speeds add up. The principle is called Galilean relativity, the idea that the laws of motion are the same in all constant velocity, non-accelerating frames of reference. But what about light? In the 1800s, scientists believed light traveled through a mysterious invisible substance called the luminiferous aether, which supposedly filled all of space. Light waves, they thought, needed a medium to travel through, just like sound needs air. If that was true, Earth's movement through this aether should slightly change how we measure the speed of light, depending on the direction we're moving through it. To test this, two physicists, Michelson and Morley, devised a brilliant experiment in 1887. They used an interferometer to detect tiny differences in the speed of light depending on Earth's motion. They expected a measurable shift. They found nothing, no matter how they oriented their apparatus, or when they ran the experiment. Light always traveled at the same speed. This was a bombshell. The idea that the speed of light was always constant, regardless of the observer's motion, didn't fit Newton's framework. It couldn't be explained by Galilean relativity, and if light didn't obey the old rules, then the old rules might be wrong. Most physicists were puzzled. Some thought the experiment must be flawed. Others tried to patch Newtonian physics with new theories, stretching and bending it to avoid collapse. But none of those efforts stuck. Then, in 1905, a 26-year-old named Albert Einstein, working in the Swiss Patent Office, published a paper titled On the Electrodynamics of Moving Bodies. It didn't just challenge Newton's ideas, it redefined space and time themselves. Einstein proposed something radically simple and deeply unsettling. The laws of physics are the same in all inertial frames, and the speed of light is always constant, no matter how fast you're moving. If that's true, then something else had to give. Time couldn't be absolute. Space couldn't be fixed. They had to shift, to bend and stretch in response to motion. Suddenly, the clockwork universe was no more. A new picture began to emerge, one where time slows down, lengths contract, and simultaneity becomes relative. This was the birth of special relativity, and with it, the end of the Newtonian era. But we're getting ahead of ourselves. First, we need to understand what it means to live in a universe where motion is relative, but light is not. In the next chapter, we'll step inside this new world, where the rules are unfamiliar, but the logic is unbreakable. Chapter 2. The Birth of Special Relativity. What if time isn't the same for everyone? What if your ruler shrinks as you move faster? And what if two events that seem simultaneous to you don't seem simultaneous to someone else? These questions aren't science fiction. They are the foundation of special relativity. In 1905, Einstein introduced the world to a new way of thinking. His theory of special relativity, special because it applies to objects moving at constant speeds, wasn't based on complex math or elaborate experiments. Instead, it was rooted in two bold postulates. First, the laws of physics are the same for all observers in uniform motion, whether you're floating in deep space or cruising in a train at constant speed. Second, the speed of light in a vacuum is always the same, about 299,792 kilometers per second, no matter how fast you're moving or in which direction. Simple enough, right? But these postulates lead to consequences that are anything but intuitive. Let's start with simultaneity. the idea that two events can happen at the same time. In everyday life, this seems straightforward. If two lightning bolts strike opposite ends of a field at the same moment, we say they were simultaneous. But what if you're moving past that field on a fast train? Here's Einstein's famous thought experiment. Imagine a train moving quickly along the tracks. Two lightning bolts strike, one at the front of the train, one at the back, and they hit simultaneously according to someone standing on the ground. But someone inside the train moving forward is getting closer to the spot where the front bolt hit, and farther from the rear strike. Since light travels at the same speed in all directions, the person on the train will see the front flash before the rear one, and conclude that the bolts were not simultaneous. Who's right? Both observers are, because in special relativity, simultaneity is relative. Two events that are simultaneous in one frame of reference may not be in another, and this is just the beginning. Let's talk about time. If light must always move at the same speed, then clocks, which can be thought of as devices that measure the time it takes light to bounce or travel, must tick differently depending on how fast you're moving. This leads to the mind-bending concept of time dilation. In short, a moving clock runs slower. This isn't just theory, it's been tested. Fast-moving particles called meteons created by cosmic rays in the upper atmosphere should decay before reaching the ground. But because they're moving so fast, time slows down for them, and they live long enough to be detected at the surface. We've even measured this with atomic clocks on jet planes and satellites. Time ticks differently depending on how fast you're going. Next is length contraction. If time slows down as you move, then something else has to give to keep light's speed constant, and that something is space. An object moving at high speeds will contract in the direction of motion, at least from the perspective of a stationary observer. So a spaceship zipping by at near light speed would appear shortened to someone watching it fly past. But to the people on board, nothing has changed. Again, it's all relative. This isn't just mathematical trickery, it's a deep feature of reality. At high speeds, space and time stretch, bend and twist to preserve the constancy of light's speed. The faster you move, the slower your time flows, and the more compressed your world becomes. One of the most famous demonstrations of these effects is the twin paradox. Imagine two twins, one stays on Earth, the other travels at near light speed to a distant star and back. When the traveler returns, less time has passed for them than for their sibling. They are literally younger, not metaphorically, actually. This isn't a flaw in the theory, it's a prediction, and it has been confirmed through countless experiments. Now you might wonder, if all these effects only become noticeable at speeds near the speed of light, do they really matter? The answer is yes, absolutely. Without accounting for relativity, GPS systems wouldn't work, particle accelerators would fail, and our understanding of the universe would be incomplete. Einstein's theory of special relativity shattered the illusion of universal time and space. It replaced them with a flexible framework called space-time, where the geometry of reality changes depending on how you move. And yet this was only the beginning. Special relativity could explain motion and light, but it couldn't handle gravity. To solve that, Einstein would need to go even deeper, and in doing so he would transform our understanding of gravity itself. In the next chapter, we'll step into this new curved universe and discover how falling isn't what it seems. Chapter 3. Time and Space, Reimagined. What is time? What is space? Are they separate things, or two sides of the same coin? Einstein's special relativity didn't just tweak our understanding of motion, it forced us to completely rethink the very fabric of reality. Before relativity, space was just space, a blank stage where events occurred. Time was the ticking of an invisible clock, the same everywhere, always moving forward, unaffected by your motion or location. But Einstein showed that space and time are inseparably linked, part of a single unified entity, space-time. Let's break that down. When you walk down a street, you move through space, left, right, forward or backward. But even if you sit perfectly still, you're always moving through time. You can't stop it. You can't escape it. And in the world of relativity, your motion through space affects your motion through time. Here's the key idea. The faster you move through space, the slower you move through time, from the perspective of someone standing still. This is not a metaphor, it's a measurable fact. Let's bring in one of Einstein's most famous thought experiments, the light clock. Imagine a clock made of two mirrors, facing each other, with a single beam of light bouncing between them. Each tick is the light bouncing from one mirror to the other. Now place that light clock on a moving train. To someone on the train, the light still travels straight up and down between the mirrors. Tick, tock, tick, tock. But to someone watching from the platform, the train and the clock is moving. So the light beam traces a diagonal zigzag path, a longer route. Since light speed is always the same, a longer path means more time between ticks. From the perspective of someone outside the train, the light clock is ticking slower. This isn't because of mechanical delay, it's because time itself is stretching for the person moving with the train. That's time dilation, in action. Now imagine taking this to extremes, a spaceship traveling close to the speed of light. From the perspective of someone on Earth, the astronaut's time slows dramatically. Years might pass on Earth, while just months tick by on the ship. If you think this sounds like science fiction, remember, this effect has been measured with real atomic clocks aboard airplanes and satellites. It's real, it's built into the math of relativity, and it's built into the systems we use every day. This strange blending of space and time leads us to the concept of space-time, a four-dimensional stage where everything happens. 3 dimensions for space, 1 for time. But unlike the Newtonian view, these aren't separate, they interact. Motion through space changes how you experience time. It's as if the universe gives you a kind of speed budget. The faster you go through space, the less speed you have left to go through time. This helps explain the twin paradox which we touched on in the last chapter. One twin travels through space at near light speed, the other stays on Earth. Because the traveling twin is moving faster through space, they move slower through time. When they reunite, one has aged more than the other, and that difference isn't just theoretical, it would be visible on their faces, written into their bodies. Another consequence of space-time is the relativity of simultaneity. In the Newtonian world, time is like a universal metronome, ticking the same everywhere. But in relativity, 2 events that happen at the same time, for one observer, might not be simultaneous for another moving observer. This shatters our intuitive idea of a single shared now. In fact, there is no universal present moment, no cosmic clock telling everyone what time it is. Your now might be someone else's past or future, depending on how fast you're moving and where you are. It's unsettling, but beautiful, and it sets the stage for a profound shift in how we think about the universe. Because if motion through space affects time, and time is just one part of a larger whole, what happens when something else, say, gravity, begins to twist and shape space-time itself? That's where we're headed next. In Chapter 4, we'll explore one of Einstein's most audacious insights, that gravity isn't a force pulling on objects. It's the warping of space-time by mass and energy. Get ready to fall, literally and figuratively, into the world of general relativity. Chapter 4. Mass, energy and E equals mc squared, 3 letters, 1 equal sign, and a tiny c squared. It's the most famous equation in the world. E equals mc squared. Even people who know nothing about physics recognize it. But what does it actually mean? What's the story behind it? By 1905, Einstein had already shattered the idea of absolute space and time. But that same year, in what's often called his annus mirabilis, or miracle year, he published another paper that introduced a deceptively simple equation, E equals mc squared. In just 5 symbols, Einstein captured something extraordinary. Mass and energy are 2 forms of the same thing. Let's unpack it. E stands for energy, mass adds mass, and c is the speed of light in a vacuum. A huge number, about 300,000 kilometers per second. Squared, it becomes even more massive. So what the equation says is this: a small amount of mass can be converted into a tremendous amount of energy. Why does this matter? Before Einstein, mass and energy were considered completely separate. Energy came in many forms: kinetic, thermal, chemical, and mass was something physical, solid and distinct. You could transfer energy between objects, or change its form, but mass stayed mass. Einstein changed that. He revealed that mass itself is a concentrated form of energy, locked away, like a coiled spring. This wasn't just theory, it had consequences. Let's consider something tiny, an atom. Inside the nucleus of an atom, protons and neutrons are held together by incredibly strong forces. When certain atoms, like uranium, split in a process called nuclear fission, a small amount of their mass disappears. Where does it go? It's transformed into energy, tremendous energy. That's the power behind nuclear reactors, and more darkly, atomic bombs. In those explosions, just a few grams of matter are converted into energy, but because of the speed of light squared in the equation, even that tiny mass yields a catastrophic amount of force. But E equals mc square isn't just about destruction, it powers the sun. In the sun's core, hydrogen atoms fuse into helium. In that fusion, a small amount of mass is lost and converted into the sunlight that warms your face, grows your food, and fuels life on Earth. Every beam of sunlight is a reminder that mass and energy are interchangeable, two expressions of the same underlying reality. And here's something even more surprising. The mass of a system depends on its energy. If you heat up an object, it gains a tiny bit of mass because you've added energy. If you compress a spring, it's ever so slightly heavier than when it's relaxed. This isn't just theoretical, it's been measured with precise instruments. Mass isn't an immutable property, it's a kind of stored energy, and that energy is influenced not just by motion or heat, but even by forces within atomic particles. In Einstein's world, nothing stands alone. Time is linked to space, mass is tied to energy, and everything flows together in the geometry of space-time. E equals mc square isn't just a physics equation, it's a statement about the unity of nature. Still, as powerful as special relativity is, it leaves something out, something huge: gravity. Special relativity tells us how time and space behave when things are moving fast, but it doesn't explain what happens when things fall, or when they're under the influence of gravity. To tackle that, Einstein needed a bigger idea, one that would take him 10 years to develop. It wouldn't just modify Newton's theory of gravity, it would replace it entirely. In the next chapter we'll explore how Einstein reimagined gravity, not as a force, but as the warping of space-time itself. We're about to leave the flat planes of special relativity and enter the curved universe of general relativity. Chapter 5. Gravity gets complicated. General relativity. For over 2 centuries, gravity was the great success story of Newtonian physics. It explained the falling of apples and the dance of planets. But Einstein saw something deeper, something far more elegant. What if gravity wasn't a force at all? What if it was geometry? Let's rewind. In Newton's view, gravity is a mysterious force that acts across space, instantaneously, pulling objects toward each other. The Earth pulls on the Moon, the Sun pulls on the Earth. You drop a ball, and gravity pulls it down. Simple, intuitive, and incredibly successful. But there were cracks. For one, Newton never explained how gravity worked, only that it did. What was this invisible force reaching across the void? Why did it act instantly? And what caused its strength to change? Worse, Newtonian gravity didn't fit with special relativity. If nothing can travel faster than light, then how could gravity act across vast distances instantly? Einstein didn't believe in spooky action-at-a-distance forces. He believed in local causes, in things that made sense, step by logical step. So he asked a bold question: what if gravity isn't a force at all? It started with a simple observation, something he called the happiest thought of my life. Imagine you're in a sealed elevator, floating in deep space, far from any planet or star. Suddenly, the elevator starts accelerating upward. You feel pressed to the floor. You could place a ball in mid-air, and it would fall, as if pulled by gravity. But there's no planet nearby. You're just accelerating. Now imagine the same elevator sitting on Earth. You're not moving, but gravity is pulling you downward. Here's the thing, you can't tell the difference. Acceleration and gravity feel the same. This is Einstein's equivalence principle. The idea that being in a gravitational field is locally indistinguishable from being in an accelerating frame. It seems subtle, but it opens the door to a profound realization. Maybe gravity isn't a force. Maybe it's the result of moving through a curved space-time. Let's picture this. Imagine space-time as a giant fabric, a smooth, flexible sheet. Now place a heavy ball on it. That's a planet, or a star. The fabric bends under its weight. Now roll a marble across the sheet. It curves toward the heavy ball, not because of a force, but because it's following the curved path of space-time. This is the core idea of general relativity. Mass and energy tell space-time how to curve, and curved space-time tells objects how to move. There is no gravitational pull, Instead, objects follow the straightest possible path in a curved space, just like a plane flying over a curved Earth appears to arc when viewed on a flat map. That's why the Moon orbits the Earth, and the Earth orbits the Sun. They're not being pulled, they're moving along geodesics, the natural straight-line paths in a curved spacetime. This idea replaced Newton's force with geometry, a bold shift that made stunning predictions. One of the first tests came in 1919, during a total solar eclipse. According to general relativity, the Sun's mass should bend the path of light from distant stars, causing their positions to appear shifted in the sky. And that's exactly what astronomers observed. For the first time in history, a scientific theory had predicted something invisible, intangible, and then been proven correct on the cosmic stage. Einstein became an international celebrity overnight. But this was only the beginning. General relativity predicted much more: gravitational time dilation, where time runs slower near massive objects; gravitational lensing, where light bends around galaxies; black holes, where space-time is curved to an infinite degree; and even the expansion of the universe itself. Every one of these predictions, once considered radical, has been confirmed. Einstein's theory didn't just explain gravity. It reshaped our understanding of the cosmos, from the motion of stars to the warping of time itself. But as powerful as general relativity is, it still leaves a question hanging in the dark. What happens when the tiniest scales of reality, the quantum world, collide with the vast curved fabric of space-time? In Chapter 6 we'll explore the tension between general relativity and quantum mechanics, and the search for a theory that unites them both. Chapter 6: Warped Worlds and Black Holes. By the 20th century, physics had two great pillars. One described the very large, stars, planets, gravity, space-time. The other described the very small, atoms, particles, and the strange rules of the quantum world. But here's the problem: these two theories don't get along. On one side you have Einstein's general relativity, elegant, continuous, geometric. It tells us that the universe is a smooth fabric, warped by mass and energy. It works brilliantly on the scale of stars and galaxies. It predicted black holes and gravitational waves, and it's passed every test we've thrown at it. But zoom in, way in, to the scale of atoms and subatomic particles, and that smoothness dissolves. Here you enter the world of quantum mechanics. This realm is chaotic, probabilistic, and counterintuitive. Particles behave like waves. They can be in multiple places at once. They don't have definite properties until they're measured, and they're governed not by certainty, but by probabilities. It's a universe of uncertainty, beautifully captured by the equations of Schrödinger, Heisenberg, and Dirac. Quantum mechanics describes electrons jumping between energy levels, photons behaving as both particle and wave, and particles interacting through strange virtual processes. It's the foundation of chemistry, electronics, and modern technology, and it works. Like general relativity, quantum mechanics has been tested again and again, in labs, in particle colliders, in the design of semiconductors and lasers. So what's the problem? They don't work together. When you try to apply the smooth curved geometry of general relativity to the grainy probabilistic world of quantum mechanics, the math falls apart. You get infinities, contradictions, equations that refuse to behave. Nowhere is this conflict more dramatic than in a black hole. In general relativity, a black hole is a region of space where gravity has become so strong that not even light can escape. At its center is a singularity, a point of infinite density where space-time curves infinitely. But infinite density, that's a red flag. Nature doesn't like infinities. They're signs that a theory has reached its limits. Here's the problem: a black hole has immense gravity, the realm of general relativity, but it's also incredibly tiny, the realm of quantum mechanics. To truly understand what happens at the heart of a black hole, or at the birth of the universe during the Big Bang, we need a theory that can combine both. This is the holy grail of modern physics, a theory of quantum gravity. It's not for lack of trying. One candidate is string theory, which imagines that all particles are actually tiny vibrating strings. Different vibrations produce different particles. It has the mathematical elegance to potentially unite gravity and quantum mechanics. But so far, no experimental proof. Another approach is loop quantum gravity, which tries to quantize space-time itself, to treat the fabric of the universe as made of tiny loops or grains, like atoms of space. Other physicists look to quantum field theory in curved space-time, trying to understand how quantum fields behave in a relativistic world. This led to one of the most astonishing predictions of all, Hawking radiation. The idea that black holes can slowly evaporate, emitting particles due to quantum effects near their event horizons. It was a moment where the two theories briefly shook hands, where quantum rules operated in curved space-time, and produced a real testable consequence. But a full union, we're not there yet. Today we have two spectacularly successful theories, and a frustrating gulf between them. Think of it like this: we have two maps. One shows the world at the scale of cities and roads, the relativistic map. The other zooms into the scale of atoms and molecules, the quantum map. Both are accurate in their own domains, but there's no single map that shows both scales at once. And until we have that map, that unified theory, we won't fully understand what happens in the most extreme corners of the universe. The birth of the cosmos, the center of a black hole, the true nature of time and space. In the next chapter, we'll step back from the equations and look at the real-world evidence. How do we test these ideas? What have we observed in the cosmos that supports Einstein, and what might challenge him? It's time to leave the blackboard behind and turn our gaze to the stars. Chapter 7: The Expanding Universe. It's one thing to write beautiful equations, it's another to prove they describe the real world. Einstein's theories were bold, revolutionary, but were they true? Science doesn't bow to elegance, it demands evidence, and Einstein delivered. Let's go back to 1915, when Einstein finalized his theory of general relativity, the idea that gravity is the curvature of space-time caused by mass and energy. Soon after, he made a prediction: if his theory was right, then the path of light would bend near a massive object, like the sun. Not just metaphorically, but literally. Light would follow the curved space-time around it. This was an outrageous idea. Under Newtonian physics, light, which has no mass, shouldn't be affected by gravity at all. But Einstein said otherwise. Into the solar eclipse of 1919, British astronomer Sir Arthur Eddington led an expedition to observe the eclipse. During totality, when the sun was blotted out, they photographed stars near its edge. According to general relativity, their light should appear slightly shifted, bent by the sun's gravity, and that's exactly what they saw. The stars appeared out of place, shifted by precisely the amount Einstein predicted. It was the first major confirmation of general relativity. The headlines were electric: Einstein's theory triumphs. The shy, obscure patent clerk became a global icon overnight. But that was only the beginning. Let's walk through a few of the experiments and observations that have tested and confirmed Einstein's ideas. 1. Gravitational time dilation. Einstein said time runs slower near massive objects. That sounds bizarre, until you realize your phone's GPS system literally corrects for this every second. Satellites orbiting Earth are further from its mass, so time ticks a bit faster for them than for you on the ground. If engineers didn't account for that tiny difference, your GPS location would drift by kilometers every day. What was once a theoretical prediction is now a tool millions of people use to get to the grocery store. 2. The precession of Mercury. Before Einstein, astronomers noticed something strange. The orbit of Mercury was drifting, ever so slightly, in a way Newton's laws couldn't explain. General relativity nailed it. Einstein's equations predicted exactly how Mercury's orbit would precess or rotate over time, due to the curvature of space-time near the Sun. It was a small effect, but a powerful proof. 3. Gravitational redshift. Light escaping from a massive object should lose energy, not by slowing down. Light always moves at the same speed, but by stretching its wavelength. That means it shifts toward the red end of the spectrum. This effect has been measured in laboratories and observed in the light from massive stars. Again, the prediction held up. 4. Gravitational lensing. Einstein predicted that massive objects like galaxies or black holes should bend light from more distant objects behind them, like a cosmic magnifying glass. Today, we've photographed this happening. The Hubble Space Telescope and other observatories have captured stunning images of gravitational lenses, multiple images of the same distant galaxy warped and duplicated by space-time curvature. It's not just confirmation, it's breathtaking. 5. Gravitational waves. This is the big one. Einstein predicted that violent cosmic events, like black holes colliding, would create ripples in space-time. These ripples would travel across the universe like waves on a pond. For a century, this was just a prediction. Then, in 2015, the LIGO Observatory detected a signal, a faint rising chirp from two black holes merging over 1 billion light-years away. That chirp wasn't sound. It was space-time itself vibrating, exactly as Einstein said it would. Since then we've detected dozens more. It's opened a whole new window into the universe. Each of these discoveries, big and small, is a vote of confidence in Einstein's vision. Not because we want it to be true, but because nature agrees. His theories continue to pass every test. But science isn't about final answers. It's about asking better questions. And there are still mysteries Einstein's equations don't answer. What exactly is dark matter? What causes dark energy? The force accelerating the expansion of the universe? What happens inside a black hole, or at the moment of the Big Bang? In the next chapter we'll travel even further, to the frontiers of modern physics, where Einstein's legacy guides us, but where new revolutions are waiting. The universe still has secrets. Let's go find them. Chapter 8. Relativity in Daily Life and Modern Science. We followed Einstein's equations from falling apples to bending light, but the same math that explains everyday gravity also points to some of the strangest, most extreme phenomena in the universe: black holes, warped time, and perhaps even time travel itself. Let's begin with the most mysterious objects in the cosmos: black holes. At first they were just mathematical curiosities, odd solutions to Einstein's equations that nobody believed were real. A place where gravity becomes so intense, not even light can escape. Imagine compressing the sun down to the size of a small city. That's a black hole, pure gravitational power packed into a tiny region of space. At its heart is a singularity, a point where density becomes infinite, and the laws of physics as we know them break down. Around it lies the event horizon, the boundary beyond which nothing, no matter how fast, can return. It's a one-way door to we don't know. And yet, these monsters aren't rare, they're real. We've seen the effects of their pull. We've measured the orbits of stars whipping around invisible centers, and in 2019, we even captured the first image of a black hole's shadow, in a galaxy 55 million light-years away. That glowing ring of light wasn't a special effect. It was reality, wrapped in Einstein's math. But black holes don't just challenge our physics, they challenge our imagination. Let's talk about time. According to general relativity, the closer you are to a massive object, the slower time runs. Near a black hole, this effect becomes extreme. In theory, if you hovered near the event horizon, without falling in, a few hours for you could mean years or centuries passing for someone far away. This isn't science fiction. It's a direct consequence of space-time curvature. We call this gravitational time dilation. And yes, it's the same effect used in the movie Interstellar, which consulted real physicists to get it right. But what about going even further? What about time travel? Let's be clear, we're not talking about hopping into a DeLorean, but in the framework of Einstein's equations, certain theoretical constructs might allow time loops. One idea is a wormhole, a tunnel through space-time, connecting two distant points in space and time. If one end experienced less time than the other, you could, in theory, travel between them and arrive in the past. Einstein and physicist Nathan Rosen explored this concept in the 1930s. Their Einstein-Rosen bridge is the seed of modern wormhole theory. But here's the catch: wormholes might exist mathematically, but keeping one open would require exotic matter with negative energy, and we don't know if such matter exists. There are also cosmic strings, rotating black holes, and other exotic ideas that might allow closed time-like curves, basically paths through space-time that loop back on themselves. But every time physicists push the math that far, nature seems to fight back. Wormholes collapse, energy requirements become impossible, paradoxes arise. Einstein himself was skeptical. He often said that the universe has ways of protecting itself from such violations, a cosmic censorship if you will. Still, the mere fact that his equations allow these possibilities forces us to ask, what is time? Is it truly one way, or are we missing something deeper? Even outside of black holes and wormholes, general relativity forces us to confront strange truths. The past and future may not be absolute. There may be no universal now. The flow of time could be an illusion, a human experience layered over a timeless fabric. At the edge of black holes and the edge of understanding, relativity merges with mystery. And yet, even as it opens doors to the extraordinary, Einstein's theory leaves us with puzzles. What happens at the singularity, where time and space themselves collapse? How does information behave when it falls into a black hole? Can it ever be recovered? And what happens when you combine all this with the rules of quantum physics? These aren't just academic questions, they point towards something bigger, a deeper theory, a more unified picture of the universe, one that we don't have yet. In the next and final chapter, we'll look at where things stand today, the unresolved mysteries, the grand challenges, the new frontiers that physicists are now racing toward. Einstein's legacy is alive and well, but the story isn't over. Chapter 9. Einstein's legacy. Einstein gave us a new language, one written in curved space, stretched time, and the deep unity of mass and energy. His equations reshaped our universe. But even Einstein didn't have the last word, because today the most important questions in physics remain unanswered. Let's step back. General relativity describes gravity and the large-scale structure of the universe. Quantum mechanics governs atoms, particles, and the micro-world. Both theories are stunningly accurate, and yet they don't speak the same language. We've spent a century trying to unite them, to create a theory of everything, a framework that explains the universe from quarks to quasars. So where are we now? The quest for quantum gravity. The most urgent challenge is to quantize gravity, to build a theory that combines Einstein's smooth spacetime with the jittery quantum world. Several approaches are in development. String theory proposes that all particles are tiny vibrating strings, existing in a universe with up to 10 or 11 dimensions. Gravity emerges naturally from these strings. It's beautiful, it's elegant, but we still lack direct evidence. Loop quantum gravity takes a different path. It attempts to quantize space itself, imagining it as a fine-grained web of loops, a quantum foam. Space and time become discrete, not continuous. But this approach, too, remains theoretical. Both are promising. Neither is complete. 2. The mystery of dark matter and dark energy. When we look into space, something doesn't add up. Galaxies rotate too fast. Their visible matter isn't enough to hold them together. The solution? There must be dark matter, invisible mass that makes up about 27% of the universe. But we don't know what it is. WIMPs, actions, something else entirely. Then there's dark energy, a mysterious force pushing the universe apart, accelerating its expansion. It accounts for a staggering 68% of and we have no idea what causes it. That leaves us with a cosmic truth. We understand only about 5% of everything. The rest is hidden, waiting. 3. Black holes and the information paradox. Einstein's black holes are silent, perfect spheres. Nothing escapes, not even information. But quantum mechanics insists information can't be destroyed. This leads to the black hole's information paradox, a deep puzzle where relativity and quantum theory seem to contradict each other. Stephen Hawking suggested that black holes emit radiation and eventually evaporate. But if they disappear, where does the information go? Some believe it's encoded in the Hawking radiation. Others think it's stored at the event horizon, a concept called the holographic principle, where all the information inside a region of space is somehow recorded on its surface. This idea, born from black holes, might apply to the entire 4. The shape of the universe and its end. We now know that the universe is expanding, but how will it end? Will it keep expanding forever, growing colder and darker? A big freeze. Could dark energy grow stronger, tearing galaxies, stars, even atoms apart? A big rip. Or might gravity eventually reverse the expansion, ending in a big crunch? We don't know, but we're searching, and through it all, Einstein's equations remain at the center. 5. A new generation of tools. We now have tools Einstein never dreamed of. Gravitational wave detectors, like LIGO and Virgo, are opening a new era of astronomy.
one that listens to the universe. The James Webb Space Telescope peers back in time, toward the first galaxies. Quantum computers may one day simulate the fabric of space-time itself. And perhaps most excitingly, young minds across the world are still learning relativity for the first time, and asking the questions Einstein himself couldn't answer. Because science is a relay race, not a solo act. Einstein ran far, he lit the path, but he passed the torch. Now it's up to us. So where does that leave us? Einstein taught us that space and time are not rigid. They bend, they stretch, they ripple, they emerge from deeper truths we're only beginning to grasp. Relativity isn't just a theory, it's a window into the profound structure of reality, and a reminder that the universe is far stranger and far more beautiful than our common sense ever imagined. We may not yet have the final theory, but we have a direction, forward, toward deeper unity, toward deeper wonder, and always, toward the stars.